Good morning. I think we should start on time so we can finish on time. Today I will finish with section 3, move on to section 4, which will be rather short because we don't have much time. And then I hope to get started with section 5. And then tomorrow I think we'll have some time for supersymmetry. So let me briefly recall what I talked about yesterday. We looked at the Klein-Gordon equation, and I said that this equation the Klein-Gordon theory is not viable as a one-particle theory because of negative probability densities and also because of the problem of negative energies. And this was the reason why one had to quantize once more. That's why it was called second quantization. And what this amounted to was the following. First of all, you solve this equation classically. So you write this as in terms of a Fourier transform. So you Fourier transform this field. So you integrate over 3 momenta with a volume element which is Lorentz invariant with respect to the 4-dimensional symmetry group. And then here we have a plane wave solution labeled by 3-dimensional momenta of x. And then here we have, from the classical theory, Fourier amplitudes, which later on in the quantum theory become creation and annihilation operators for particles. So, we have this. And here I put a star. This is just a convention in some sense. So you can see here that this field has 2 kinds of amplitudes. These are the so-called positive energy solutions, which I wrote down with a positive Q0 component, and these are the negative energy solutions, and they're multiplied by independent Fourier amplitudes. This is the complex scalar field. So this is complex. And the real scalar field, we have phi equals phi star. And this is the same as saying that B equals A. So the following I will most of the time restrict attention to the real scalar field just to save time and not, so I don't have to write, because the relations which I'm going to write down for A and B are the same, and I don't want to lose too much time by writing down the same equations. So, as I explained yesterday, we think of this as a theory with infinitely many degrees of freedom, labeled by continuous infinity of parameters. And when you go over to Fourier space and quantize the theory, then these A's and B's become creation and annihilation operators for particles. So upon canonical quantization, as explained yesterday, and with some you have to do a little algebra, you find that A of Q with A of Q of P dagger is given by a factor which is conventional times the delta function. And then you have similar relations for the B's, and furthermore A with A and A dagger with A dagger commute. And given this information, we can now define the Hilbert space of the theory, or the Fock space, by introducing a vacuum state, state 0, which is defined, which is annihilated by all these operators, obeying A, Q, 0 equals 0 for all Q. And as I had explained yesterday, you can think of these things as an infinite a collection of harmonic oscillators, non-interacting harmonic oscillators, well, without interactions, and this continuous infinity is labeled by the three momenta. So then n-particle states are built by acting on this vacuum with a creation operator, and you can act with an arbitrary number of creation operators. So you can now think about an n-particle state by acting with n creation operators, Pn on the vacuum. So this state would have n particles in it with momenta P1 to Pn. But we can also multiply this and smear this out with some kind of n-particle wave function. This we can do. And we have to integrate, of course. We have to integrate over the d3p j over this factor. I always include this factor so as to keep the volume element Lorentz invariant. So this is the volume element here. So that's an n-particle state that's characterized by some kind of wave function here. Think of this as an n-particle wave function. And furthermore, in fact, this state has definite sharp particle number, but we can also write down states that have indefinite particle number by summing this from 1 to infinity. So this way we get a very complicated state. So this is a state psi in the Fock space, and this state does not even have a well-defined particle number. So you see in this theory we have the possibility of not just talking about one particle states as in ordinary quantum mechanics, but we can introduce as many particles as we like. Of course, we will insist that this state, since it's a Hilbert space, is normalizable, and when you take the square of this, the scalar product of this state with itself, you will essentially get a sum of integrals over these functions squared, and then that you will have to require to be finite norm. Well, yesterday I was asked the question, maybe I should answer it in public too. Here you start out with sort of, in the classical theory, or first quantized theory, think of this as a wave function, just like in the Schrödinger equation, and that wave function has a definite meaning in the sense that if you square it, you get a probability amplitude. But what is the meaning of this thing when I now turn this into an operator? Then you sort of lose you can no longer visualize, or it's much more difficult to visualize what this is. You can sort of get it from here, because you can now take, if you take this state, and you take a matrix, if you look at if you define a function phi of x in the following way, now this is a classical function, so this is a wave function if you like, by taking a matrix element of, say, this operator between this n particles, or this state, and the vacuum, then what will happen is that this will project out the one particle wave function that's contained in this state. And similarly, you can construct n particle wave functions by sandwiching the product of n operators between the vacuum and this state. So the way to get back to, how do you get back to an ordinary wave function using this operator, which itself is of course not a wave function in the usual sense, the recipe is simply to sandwich this operator between the vacuum and this state. It is quite true that these objects are much harder to visualize, and their meaning is much harder to understand. There's, of course, at the end of the day, in quantum field theory, you will have to produce prescriptions that tell you how to produce numbers that you can measure in experiments. And it's quite a long way from this in this formalism, from the basic objects that you're dealing with, quantum fields, to quantities that you can actually measure and compare with experiments, like scattering amplitudes. But these will usually involve, in particular, matrix elements of this sort. Well, one thing that you can also immediately see here is that we have commutation relations, and the one I didn't write was A dagger with A dagger, P, Q is equal to 0, so it means two of these creation operators commute, and that means that this wave function is symmetric, which in turn means that these particles are bosons as expected. Well, at this point, although it's just free field theory, I can already tell you about the first infinity, the vacuum energy. Well, I said this is an infinite assembly of harmonic oscillators, and you know that every harmonic oscillator has a 0-point energy, which is 1 over 1/2 h bar omega, and the total vacuum energy is, of course, the sum over all these separate contributions. So this will be something like the following. So it's d3p divided by d omega of p, and then we get a contribution from every momentum. And this is, of course, divergent. It simply means that if you have an infinite set of harmonic oscillators, their vacuum energies will sum up to give infinity. So this is the first infinity you encounter in quantum fields here, but it's a relatively mild infinity because it's just it's a sort of additive addition to the energy, and of course we're free to start counting our energies at any point where we like to start counting. So we simply renormalize it away by making subtraction from the Hamiltonian of an infinite number to get something finite. The divergences one will encounter in quantum field theory later on are of a much more difficult type. And for example, you can ask yourself, what happens if I multiply two of these operators? And so this is an infinity, but it's not so serious. But in addition, we can check expressions like phi of x to some power, say n, doesn't matter, will be ill-defined. This is a simple exercise you can do. The operator is ill-defined, or if the operator is well-defined, then all its matrix elements have to be well-defined. So all you have to check in order to see that it's not well-defined, you just calculate the matrix element of such an operator between appropriate states. Well, there's a way to make them well-defined that goes just like here. It's called normal ordering. In order to see what this is, you recall where this comes from in the harmonic oscillator. Recall that the Hamiltonian for the harmonic oscillator is, when you calculate it, it's given by A dagger, A plus A dagger. And then you write this as A dagger A plus 1/2 a dagger. I'm setting the h bar omega equal to 0. And then you see that this is the contribution that gives the vacuum energy for every single one of these oscillators, whereas this thing is well defined. So dropping this contribution, an infinite number of these contributions, is the same as replacing this expression by this expression, and this expression differs from this one by the fact that all the creation operators have been moved to the left. So the normal ordering prescription tells you that move all in any given expression like this one, you expand it out, you have the operators, the creation and annihilation operators appearing there all over the place, and you go over to the normal ordered expression by moving all the annihilation, the creation operators to the left. So this gets us obviously rid of this the divergence that comes from here, but it will also get us rid of divergences when we calculate vacuum expectation values of such operators, and thereby you arrive at something that is well defined. So roughly speaking, in this free field, in the quantum theory of the free scalar field, we already encounter infinities. These infinities are essentially related to the fact that we have an infinite number of degrees of freedom. But in free field theory, you can get rid of these infinities relatively easily, namely by normal ordering. This will no longer be true in interacting field theories, where normal ordering is not enough. You have to do other things. You have to also renormalize coupling constants, masses, and so on. Well, we're almost at the end of this chapter, but there's one more thing, or two more things I wanted to say. The canonical quantization involves going through a Hamiltonian, from the Lagrangian to a Hamiltonian description, and that involves singling out the time variable. Time translation plays a special role, and when we write down these commutation relations, phi dot or pi t of x, phi t of y equal to minus I delta t x minus y, it seems like this procedure is no longer or violates Lorentz invariance. So this is not manifestly Lorentz invariant anymore. Manifestly means to the naked eye. It would be, if it's manifest, you can immediately see that if something is manifestly Lorentz invariant, it's such that you can immediately see that it's Lorentz invariant. Namely, it just involves Lorentz invariant combinations, etc. But something where you sort of single out one coordinate, the time coordinate, and treat it differently from the space coordinate, is certainly something that's not, doesn't look Lorentz invariant. However, we can still check that Lorentz invariance is preserved. Invariance is preserved. And this you do by calculate the commutator at arbitrary times in time and space coordinates. So x with phi of y at arbitrary x and y. And in this case, you can do this calculation because, well, this expression already gives you the field, the quantum field, it for arbitrary values of x. So you start from an initial surface, and you have solved the theory when you can describe the time evolution of the operator explicitly. Now this formula is already an explicit solution of this equation. This is the way it was constructed. So in particular, it means that we can also, and this is something you have to check, that we can also describe the time evolution by the Hamiltonian. We can write something like this. So this is the free Hamiltonian of this associated with the Klein-Gordon equation. And this is the reason we can calculate this explicitly, and we can explicitly check or look whether this expression preserves Lorentz invariance or not. And what you find is with some calculation, but you just have to use the relations which I wrote on the blackboard, you find that in fact phi of x and phi of y, this is a function, or rather a generalized function, which is given by the following expression. You can write it as a four-dimensional integral e to the minus px minus y delta p squared minus m squared. And then you have an epsilon function of p0, which is plus 1 if p0 is positive, and minus 1 if p0 is negative. So this is the answer. And this is called the commutator function, depends on the mass. And this is defined like this. By the way, I should mention that this is just a function, or rather, since we're in a Hilbert space, you should think of this as the function multiplied by the unit operator. It's by no means trivial that this thing is really a number. It could also be a non-trivial operator. But in free field theory, this comes out to be a number, and we can really explicitly calculate it. And when we do the calculation, this is what we get, and this is a function. But as you can see, it's a rather singular function, because it has it has a delta function inside, it has this discontinuous epsilon function inside. So if one looks at it very closely, it's not a smooth function, but it's something more singular, like the delta function, and that's why people call this a distribution or a generalized function. Now, given this, you can check that indeed, well, first of all, you can check that this function satisfies the Klein-Gordon equation. Well, that's obvious. It was built in from the beginning with this delta function. But you can also check that delta of x m is equal to delta of lambda times x m, where lambda is some Lorentz transformation. Well, this is a little bit of calculation, which I don't want to do. This is something you can also look up in the books. But basically the reason you can do this is that you have a Lorentz invariant scalar product. This is, of course, a Lorentz invariant four volume. This expression is Lorentz invariant. And the only thing we have to be a little careful is here, because this is a function that if you draw the light cone, it's plus 1 if I draw the light cone in the t space. Then this function is plus 1 in the forward light cone, and it's minus 1 in the backward light cone. So this tells us that the function in Fourier space is supported on some kind of mass shell. And this is Lorentz invariant if we take a Lorentz transformation that does not interchange forward and backward light cone. So we have to be a little careful here and just restrict attention to such Lorentz transformations that map the forward light cone into the forward light cone, don't reflect it. But then you can see that this function too will be Lorentz invariant, because this factor tells me that everything is concentrated here on this mass shell hyperboloid. So this now establishes that this prescription, canonical prescription, does not violate Lorentz invariance, even though we start out with something that does not look like it's Lorentz invariant. Moreover, and that requires a little more algebra, you can check that indeed delta of x minus y m squared is equal to 0 if x minus y squared is less than 1. That is the commutator between two such field operators that vanishes at space-like distances. This is something I mentioned at the beginning of these lectures as one of the general postulates of quantum field theory. This is something that should also be true for an interacting quantum field theory. Even in an interacting quantum field theory, we'll still postulate this. This equation up there will be replaced by some more complicated equation involving nonlinear terms, but it should still be true that that this commutator function is Lorentz invariant and that it vanishes at space-like distances. This is the expression of causality in quantum field theory. Now, for interacting quantum field theories, of course, this is much, much harder to check. And if you cannot solve the theory exactly, the only thing you can do is check it order by order in perturbation theory. Finally, the final thing I wanted to say, something about propagators. What is a propagator of Green's function? Well, we take this equation and generalize it. So, now the chapter is, the subsection is Green's functions. Or propagators. Well, I take this function, take this equation, and instead of putting 0 on the right-hand side, I put now some source term on the right-hand side. J of x is some source. At this point, we don't want to specify. It can be, well, in principle, to keep things easy, think of this as an external source, like an external field that serves as a source for this field. Then how do you solve this equation? And, well, the answer is known, of course. You solve it by means of a so-called Green's function. Green's function. Then you define a function as m squared g of x minus x prime, such that this is equal to minus I delta 4 of x minus x prime. And by means of this Green's function, you can rewrite the differential equation as an integral equation. So this can be rewritten as phi of x is equal to, well, pi 0 of x. So this is the solution of the homogeneous equation of the equation. Homogeneous means without the source. And then we have an integral operator, which is written like this. X prime, g of x minus x prime. And I should put an I here, times j of x prime. This extra term has to do with the fact that the equation, the solution of the equation, is not uniquely determined by just giving the solution, but in addition you will have to give some kind of initial or boundary conditions. This is always the case with differential equations in physics. It's almost a universal principle. It's not just that you have to give the equations, solve the equations of motion, which are partial differential equations, but you also have to give some set of initial conditions in order to determine the solution uniquely. Well, this is something I don't want to go into too much detail, but this is related, the fact that you can add here these terms which solve the homogeneous equations, so there's still a lot of arbitrariness in the solution, is related to the fact that you must specify boundary conditions. So given this, given that you can calculate this Green function, then you can really solve this equation by integrating the source term with this Green's function. Now you can even use this can even be used classically, you can even use this for J, which is a function of phi itself. For example, phi cubed. Then of course that this doesn't really solve the equation, you've just rewritten the differential equation as an integral equation, but the advantage of this equation is that you can iterate it. So you write this like this, and then you substitute, and then for the phi which occurs in here, you again substitute, and in this way you get an infinite series that expresses, that solves, that gives you a solution for this equation. Well, so all we have to do is solve this equation here, and this is done by going to Fourier space, solve, so we call this star, solve star by going to Fourier space, and by doing so, you find that this is equal to g of x equal to 1 over 2 pi over 4. So I should put an I here. I d4p times e to the minus ipx p squared minus n squared. Well, this is some integral which we can actually solve, but we still have to specify something, because we can write p squared minus m squared as p0 plus omega of p times p0 minus omega of p. And then you can rewrite this as g of x becomes equal to 1 over 2 pi over 3, 2 pi to the power 3, d3p divided by 2 omega of p. So all I've done now, I split the integral into an integral over the time, the zero component and the spatial components of the momentum. So dp0 plus 2 pi. And then this is equal to pi 0 plus omega of p 1 minus pi 0 minus omega of p. And then, in principle, I cannot do this integral, but as you can see, this is an integral over the variable p0, which is real, and there will be poles at omega of p and minus omega of p. So if we draw, well, this is the p0 axis. We now extend this to the complex plane, and then we see that this integral will have, this integrand will have poles at omega of p and minus omega of p. Now, in order to specify the value of this integral, you will have to you need an instruction on what to do about these poles. And this is, of course, why I introduced the complex plane. The prescription will be such that whenever we encounter a pole, we will have to specify whether we encircle it, we go below it, or we go above it. And of course, there are various ways of doing this. For example, you can shift both these poles into the upper half plane. You can shift them into the lower half plane. And then you will get different answers, and the answers for the Green's function will differ precisely by such a term which solves the homogeneous equation. Now the prescription, which is the relevant one for quantum field theory, is the one that was given by Feynman, and the prescription is the following. In order to make this integral well defined, you introduce an infinitesimal imaginary contribution here, and then here we have F for Feynman. And if you look at what this does in terms of these poles, it shifts these poles into the complex plane in such a way that this pole gets shifted upwards here, and this one gets shifted downwards. And then the prescription is you do the integral with these slightly shifted poles. You do the integral, and when you finish with the calculation, you take epsilon to 0. This is why in some books, like Landau-Lifshitz, you will find the notation, this notation, which is, seems like it's a little paradoxical, but what is meant here is that you've shifted a little bit into the complex plane, do the calculation, and then take the limit epsilon to 0. And by doing this, then you have to, oops, I forgot factor here. You can then calculate the integral by closing the integration contour either in the upper half plane or in the lower half plane. Which one you pick, of course, depends on this factor here. You have to close it in that direction, where you have an exponential damping of this factor. And when you do this, this comes out to be the following, namely 1 over 2 pi. So this is now for Feynman, GF of x is equal to 2 pi of 3 d3p divided by 2 omega of p times, well, there's now a theta function here. This is the contribution that you get if the time coordinate is positive. So e to the minus I omega t plus I p x, where the omega is, of course, always the omega of p, plus theta of minus x0 e to the I omega t minus I p x. So this is what you find when you do this calculation with this prescription of shifting the poles into the complex plane precisely in this way. If you do it in another way by shifting both poles into the upper half plane or both poles into the lower half plane, you get another kind of propagator in so-called, or Green's function, the so-called advanced and retarded Green's functions. You may remember from electrodynamics, but the one that seems to be relevant or is relevant in quantum field theory is this one. And as you can see, this is such that for positive time, only positive frequencies or positive energies contribute, and for negative times, it's only negative frequencies that contribute. And it's now a little exercise to show that this Green's function is also equal to an expectation value, namely, so this is exercise factor I times a vacuum expectation value of a product of two field operators, and phi of x and phi of y. But this is not quite what this is, but rather we have to introduce an additional modification here, so-called time ordering prescription. Time ordering means that we order the operators according to whether the arguments, time arguments, in the order of the time arguments, such that if the x time component is bigger than the y time component, we write it like this. Or if it's the other way around, we write it in the other order. Well, Feynman was, of course, led to introduce this Feynman propagator, or this special choice of Green's function, by very physical considerations. But in quantum field theory, later on, when you get to the calculation of S-matrix elements, it also comes out this way, that the relevant expectation values that you have to compute are the ones that involve time ordering, that is vacuum expectation values of time order products of operators. At this point, we'll I just wanted to mention it, because first of all, this propagator appears as a special solution of this equation on the one hand, and this is the way it's described, for example, in the old textbook by Bjerke and Drell. But on the other hand, when you calculate vacuum expectation values in quantum field theory, it turns out that the product of the time ordered product of two, the time ordered product of two scalar field operators is given by this very same function. So this was a crash course for the scalar field quantization. This is actually something that in an ordinary course would take me 2-3 weeks to lecture about, because I would have to fill in the details in all these places. But with you, I assume that you have heard it already. There's some time I've heard, you must have heard this before, and you must have seen it before, and so maybe you should think of this as a refreshment course. But the scalar field is still nice because it's a rather simple example that shows you how quantum field theory works. Now, there are more kinds of fields, of course, we know, in nature. There's not just the scalar fields. In fact, so far, there are no scalar fields at all. Maybe they will be discovered at lab soon. But so far, all the fields that we see in nature, or particles that we see in nature, are of a more complicated kind. And that is because they have a spin. So now we have to proceed to higher spin. Spin 1/2. In this case, we will have to deal with the Dirac equation. So that's certainly a necessity for anyone who wants to do quantum field theory and elementary particle physics. But it's an equal necessity to understand spin 1, massless, this will lead to Yang-Mills theories. Now, at the free level, these I can also describe these fields as collections of harmonic oscillators, but the fact that you have spin means that you also have some kind of polarization. It's just like, for example, in electrodynamics, the basic fields are electric and magnetic fields, and these fields have a polarization in space. And the same is, of course, true for the photon field itself, which is a 4-vector. And the reason this is, even at the level of the free theory, this is more complicated, that you have to deal with these extra components. You will have to introduce polarizations and so on, and all this will clutter up the notation. Now here, an extra effect is needed, namely because these are massless fields, we'll have to devise a way of getting rid of the helicity zero state, and in order to do that, we need gauge invariance. So that complicates life even further. Gauge invariance. And if you go to spin 3/2 and so on, it gets even more complicated. So we'll stop here, and I'll say a few words about the Dirac equation. As I mentioned before, you should probably think of this as a refreshment course, because I cannot possibly explain all this in detail. But I'm sure that you've all looked at the classic textbook by Bjerken and Schell, Volume 1. That's the real classic. Volume 2 is the one about quantum field theory, and that is probably less read because it's more formal. So, Dirac equation is, in my conventions, written like this: psi of x equal to 0. Now, what is gamma mu? Those are the gamma matrices. Gamma mu are 4x4 matrices obeying the following relation. Gamma mu is equal to 2 eta mu. And you can give them very explicitly. For example, you can choose it such that this is the following matrices. They're 4x4. I can write them as 2x2 blocks of 2x2 matrices. And one choice, one convenient choice, is the following. So here we take the Pauli matrices, 2x2, and here's a minus sign, sigma I 0. But that is, of course, just one choice. There are many other equivalent choices. I was once told that Fermi, one of the grand physicists of our century, he never used this kind of notation. He had a notebook where he had written out all the gamma matrices, really as 4x4 matrices with all the entries. And he never used this kind of covariant notation. So that means that these matrices have matrix indices, alpha, beta, running from 1 to 4, which I will not write out anymore, but well, I'll write them out once just to make clear what I'm talking about. So this thing is a 4x4 matrix, but at the same time a differential operator. So here you should think the unit matrix in this four-dimensional space, and this acts on this object psi b of x. So this is the Dirac wave function having 4 components. So that's already a technical complication, because here we have just one scalar, and all of a sudden we have a field that has 4 components. We now know what these 4 components are associated with. Since we have spin 1/2, we need 2 polarizations, plus 1/2 and minus 1/2, with respect to some chosen axis. So that explains 2. And the other 2 are needed for, well, I interpret it as being related to antiparticles. So the Dirac field in this equation describes the electron with 2 spin states and the positron with another 2 spin states, which makes altogether 4 components. Well, we also need the notion of a conjugate spinner. Called written as psi bar, and defined like this. By the way, I should also say that the hermiticity properties are such that this is Hermitian and this is anti-Hermitian. This, of course, has to do with the minus signs of the Minkowski metric. But you can show that all of this relations can be conveniently written as follows. Gamma mu dagger is equal to gamma mu Comma 0, as you can check. Then it turns out that there's a conserved, from this equation, you check that there's a conserved current. Current, J mu, is equal to psi bar gamma mu psi. Obeys J mu is equal to 0. Now you can see why Dirac was excited about this. And this is what the argument I already mentioned yesterday, that whereas for the scalar field, the current has this derivative inside, which prevents this thing from being positive definite. You can see that if you look at J0, this is psi dagger times gamma 0 times psi. Then this squares to 1, so this is psi dagger, which is positive definite. Well, that's very nice, but in some sense it's also a mirage, because there's still no way to interpret this as a one-particle theory because of the negative energy problem. By the way, I think at this point you should tell me if I'm too fast, or I necessarily have to skip over things here, assuming that you've heard some of this before. There's now a whole technology, because it has to be developed. I had the expansion of the Fourier expansion of the free field, scalar free field here on this side of the blackboard, and we have to repeat the same exercise for the Dirac field. And then we have 4 kinds of solutions again, 2 positive. So we go to Fourier space, and then we solve this equation in Fourier space. Then we just have gamma mu p mu minus m. It's just an ordinary matrix equation. And again, this solution will be supported on the mass shell hyperbolic p squared equals m squared. And so we get 2 kinds of solutions, or plane wave solutions. There are 2 kinds. You can look them up in the books if you want to. They're written like this: UR of P and VR of P, where alpha each. So each of these has 4 components. The U's are the positive energy solutions, and the V's are the negative energy solutions. And this label R is 1, x 1, 2, labels the spin state. In order to really see this, you will also have to introduce some kind of spin projection operator, which I don't want to do here. I just want to mention that this altogether we will have 4 solutions. And given those 4 solutions, we can then write down a mode expansion for the Dirac field, which is very similar to the mode expansion for the scalar field. So from this we get a mode expansion. Which is as follows. It's a little more complicated to write than for the than for the scalar field. This factor again. Then we have to sum over the spin states, so R equals 1, 2. We again have the invariant volume element. Well, let me write it like this. This is not the standard normalization, but here we don't want to discuss normalization factors. And now we have A R of P times U alpha R of P times e to the I omega of P times T minus P x plus And again, now we put a dagger of P times V, alpha of R, P, e to the I, omega of P times P minus Px. So this is now the expansion of an arbitrary solution of this equation into Fourier modes. Well, as I said, these things you can look up in Birkin and Drelfer's volume. This is a standard thing. So what do we have here? So here we have again the positive energy solutions. Here we have the negative energy solutions. We have the label momentum. By the way, I can really write this as P because the energy which appears here will of course be the omega of P. Well, and then these things here are again the Fourier amplitudes. Fourier amplitudes. And before I said that for the scalar fields we had the A and the B, and that these were creation and annihilation operators for upon quantization for harmonic oscillators. And you should think of this in the same way, except that instead of just one creation and annihilation operator, we now have two, four, or altogether four, namely A and B. So this is completely analogous to the, let me write, for the phi we had here, we had the A, and here we have the B dagger. You can also, well, this was the complex scalar field, and this is a complex spinor, of course, and I said that a real scalar field, uncharged scalar field, will be described by something, by real, well, uncharged particles are described by real scalar fields for which A is equal B. In principle, we can also have a spinor where this A equals B. In this case, we have a Majorana spinor where again particles are equal to antiparticles. There's some possibility that neutrinos are of this type. So this is the Fourier expansion, the mode expansion, and now again we have to go through this procedure called canonical quantization. And this is technically slightly more complicated. First of all, because of these, because of the spinorial nature of the field, but also because the Lagrangian from which you get this is first order in the derivative. And if you look at it very closely, then you will see that this is a Hamiltonian system which is not completely obvious to treat because it has constraints. But this theory was again developed by Dirac, and so you start from a Lagrangian, you go to the Hamiltonian, define canonical momenta, and so on and so on. And then we want to find out what are the relations for these objects. Well, as you all know, at some point the spinorial nature comes in, and at some point you will have to decide whether this field obeys commutational or anti-commutational relations. Now you all know that fermions obey anti-commutational relations, and let me briefly recall where this comes from, because after some calculation you find that the Hamiltonian is proportional to some r, and then you have this integral again with a measure d3p over omega 2p times omega of p, and then it's AR dagger of p, AR of p, and now you find that here you get a minus sign. This is really a crucial minus sign. Minus signs, well, are crucial and not so crucial minus signs, but this minus sign is really crucial. So this is minus, and for the bosons, we would have a plus here for bosons. So it's minus, I have 2 minutes, I'll be finished. So it's minus here for fermions. And this comes out after a longer calculation, where you also have to use properties of these U's and V's. Now, for the bosons, we have this calculation for the harmonic oscillator, A dagger A plus A dagger, and then we imposed the commutation relation, and it was A dagger A plus a number. Now, what would happen if we simply imposed commutation relations here? We would rewrite this as A dagger A, B dagger B, throwing away an infinite constant, but the minus sign would still be there. And that would mean that this Hamiltonian operator, as it stands, would not be positive definite. You would have a term which would be positive definite, where you could increase the energy to as large values as you would like. And here you would have a term which would allow you to make the energy as negative as possible. And this is again reflection of the fact that you have the classical theory, these negative energy solutions. And the only resolution of this dilemma is impose anti-commutation relations. This is called canonical anti-commutation relations. And so these in particular, we require that A R of P, A S of Q is proportional to factors don't matter, delta RS, delta 3P minus Q, where this means, this means A of R, A of S, dagger, plus A of S, dagger, A of R. So here we have a plus sign instead of a minus sign for the commutator. And when you do this, you can check that this gets replaced by a term with B dagger B, but with a plus sign in front. And this finally is the resolution of this negative energy problem in quantum field theory. And it's something that you cannot really do in the classical theory, even though you might think we have this extra hypothesis of a field hierarchy, but which in some sense is equivalent to this. But here you see that you have a crucial minus sign here that forces you to postulate anti-commutation relations rather than commutation relations. And then, maybe I can just finish in two sentences. Now you can go again to the same procedure as for the scalar field. You can define a vacuum, you can define excited states, and then due to this plus sign, you will find that the particle wave functions have to be antisymmetric upon interchange of two arguments. So this also leads to the Fermi statistics. Now, it's a general theorem of quantum field theory that this is generally true if you have spin 1/2 or spin 3/2. You always have to impose anti-commutation relations, and you always end up with Fermi statistics, whereas if the spin is integer valued, you always have commutation relations, and you end up with Bose statistics. Here it came out as a special case, but this is one of the few rigorous results of quantum field theory. It's called the spin statistics theorem, and tells you it's always true. If you start, for example, with the gravitino and go through this mode expansion, which is even more complicated, go through all of this, it means at the end of the day, you will have to impose anti-commutation relations. And you will end up with a field obeying Fermi statistics. So, to summarize, in quantum field theory, all these quote-unquote paradoxes of the classical one-particle, first quantized theory get resolved. Well, I didn't get to interactions, so tomorrow I will talk about how to construct interactions, how to limit their number to the useful ones, and then I'll say something about supersymmetry. Thank you.